react to this change in lift?
The pressure enthalpy chart for a two-stage centrifugal chiller is similar to a positive displacement machine, except for a few additional points created by the flash economizer. Heat of compression is reduced from points 2 to 3 due to the refrigerant gas introduced by the flash economizer, while points 7 and 8 show the liquid vapor separation in the economizer caused by the first expansion device. One other difference is a lack of subcooling at point 6 due to the cycle process. Just like positive displacement compressors, power consumption is increased due to the higher pressures associated with heat recovery. However, the differences in the pressure enthalpy chart between a positive displacement compressor and a centrifugal compressor are not important when heat recovery is concerned, but the physical differences in the compressors themselves are. The first key point to keep in mind is that there is no physical component that forces refrigerant through a centrifugal compressor. The refrigerant flowing through the compressor is its own driver and its own inhibitor to prevent refrigerant from flowing in the wrong direction. This mode of operation makes centrifugal compressors very efficient at their design point, but how they react to differences in lift and refrigerant flow are quite different. The possibility of surge is another factor that has to be considered. A centrifugal compressor uses the principle of dynamic compression, which involves converting one form of energy to another. In this case, the conversion of kinetic energy to static energy increases the pressure and temperature of the refrigerant as it moves through the compressor. This process is achieved through the use of a rotating impeller. First, the center, or eye of the impeller, draws refrigerant vapor into its internal radial passages. The rotation of the impeller accelerates the refrigerant as it travels through the passages, increasing the velocity and kinetic energy of the refrigerant. After leaving the impeller, the refrigerant vapor continues through a stationary diffuser passage where it eventually widens out into the volute. The larger cross-sectional area of the volute causes the refrigerant to slow down in order to maintain the same flow rate. As the velocity decreases in the volute, the kinetic energy is converted to static pressure. The principle of dynamic compression is difficult for some people to understand. Why would refrigerant pressure simply increase due to velocity changing? Dynamic compression is similar to the static regain method used in duct design, where velocity pressure is converted to static pressure. Let's look at the velocity-pressure relationship that acts on the refrigerant vapor. You can see that these forces can be broken down into two primary components. One is the radial vector, V sub r, which is proportional to the refrigerant flow rate through the compressor. The other is the tangential vector, V sub t, which is proportional to the rotational speed and the diameter of the impeller. Together these form the velocity vector r, which is proportional to the kinetic energy of the refrigerant. Therefore, the ability of a compressor to produce static pressure can be changed by the refrigerant flow rate, rotational speed, and diameter of the impeller. For heat recovery, the compressor must produce a larger pressure differential between the evaporator and condenser as compared to a standard cooling application. Since the refrigerant flow rate is indicated by the chiller's cooling capacity, the higher pressure requires a larger diameter impeller, or a higher rotational speed if the compressor is gear-driven. The relationship between temperature and power consumption for a centrifugal compressor can be seen here. Starting with 85 degree entering heat recovery temperature, a chiller with the same heat exchanger shells and compressor can maintain the same cooling capacity up to a 100 degree entering heat recovery temperature at the same 20 degree delta T. This assumes the impeller diameter was allowed to increase with the higher temperatures. The additional power required to perform heat recovery is shown in relation to that same identical chiller operating at ARI conditions. One thing to also consider is that a chiller becomes more inefficient in cooling mode as the heat recovery impeller diameter is increased. So as heat recovery temperatures rise, the chiller efficiency decreases in both heat recovery and cooling mode. When performing an energy analysis, be sure to take into account the chiller's efficiency reduction and the amount of heat recovered. As already mentioned, standard cooling efficiency is reduced with the larger impeller diameters required for heat recovery. For this reason, variable speed drives are sometimes considered for heat recovery chillers. If a chiller spends most of its time in heat recovery mode, higher lift requirements limit these savings because the drive can't slow down. It is also important to know that incoming water temperature for the standard cooling condenser has no impact on chiller efficiency when in heat recovery mode. Even if you can lower the cooling tower set point, the heat recovery condenser still requires the same amount of lift to reject the same amount of heat. Also remember that a variable speed drive saves energy by riding the surge line of a centrifugal compressor. Since heat recovery is more prone to compressor surge, adding another variable into this equation is not always recommended. We'll cover the details of surge in a few minutes. The slide shows a quick example of what was presented on the previous graph. Here, two chiller selections are shown. One selected for cooling only and another selected for heat recovery with 105-degree leaving water. The same compressor and shells were used on both of these selections, only in the impeller size was allowed to change. In this case, a cooling only chiller was selected with a COP of 6.2. The same chiller with the larger impeller and heat recovery condenser is now at a 5.6 COP when in cooling mode. The even lower COP value in heat recovery mode is expected due to the higher lift requirements. Due to the larger impeller size, the efficiency of the heat recovery chiller in cooling mode is reduced compared to the cooling only chiller. When using centrifugal chiller in a high lift application, it is extremely important to understand compressor dynamics at part load. Larger pressure differentials challenge the ability of a compressor to unload due to a condition called surge. Consider a constant speed compressor impeller and the velocity vector that were discussed earlier. As the load on the chiller decreases, the inlet vanes restrict the refrigerant flow into the compressor. This decrease in the refrigerant flow reduces the radial vector V sub r. In this case, the tangential vector V sub t decreases as well. Now, why would V sub t decrease with a constant impeller speed? We know that the impeller can't magically change diameter inside the compressor. V sub t becomes smaller due to the pre-swirling of the refrigerant caused by the inlet vanes. Since the refrigerant is already rotating as it enters the compressor, the effective rotational speed seen by the refrigerant is reduced. If variable speed drives are brought back into the picture, V sub t could also be reduced due to the slower compressor speeds. When both vectors are reduced at part load, the resultant velocity vector r, which is proportional to the kinetic energy, is also reduced. As the load is further reduced, the velocity vector can eventually reach a point where the kinetic energy of the refrigerant is no longer large enough to overcome the static pressure in the condenser. When this occurs, the refrigerant vapor flows backwards through the diffuser passages and into the impeller. This instantaneously reduces the pressure inside the impeller passages, allowing the compressor to reestablish the proper direction of refrigerant flow, only to repeat the process again. This unstable condition is known as surge. The refrigerant continues to flow backwards and forwards through the compressor, generating noise and vibration. Prolonged surge is not good for the compressor and should be avoided. To avoid surge on an existing chiller, you can either increase the refrigerant flow or reduce the lift. Sometimes surge on a heat recovery machine is prevented by maintaining a large cooling capacity and high heat rejection through the heat recovery condenser. Sometimes chilled water reset is performed. If your heat recovery chiller is operating during cooler months, dehumidification might not be as high of a concern. But the primary issue that needs consideration is whether you regulate your heat recovery capacity on the entering water temperature or the leaving water temperature. For centrifugal chillers, you need to target the entering heat recovery temperature. The curves on the graph represent the performance of a typical two-stage compressor over a range of inlet vane positions. The dashed line that runs across the top and to the far left of the vane curve is the surge boundary. The important items to remember on the graph are point A, which is your design heat recovery operating point, and the unloading lines AC and AB. Now let's look at the graph with all the extra clutter removed. Here's the same graph, but now we're only looking at the two unloading lines and the surge boundary. By looking at this graph, it becomes clear why you maintain a constant entering heat recovery temperature. Maintaining the leaving heat recovery temperature doesn't give the centrifugal compressor any lift reduction, and then the unloading line, AC, shows how quickly you can run into problems by controlling the chiller this way. The line AB shows unloading by maintaining a constant entering heat recovery temperature. With this control strategy, the leaving heat recovery temperature is allowed to float up and down in response to the chiller's cooling load or required heating capacity. By allowing the leaving heat recovery temperature to float, you give the chiller some lift reduction and allow it to unload more successfully. Now this seems counterintuitive for a heat recovery chiller's application. For example, if you specify a certain leaving hot water temperature of 110 degrees, you want 110 degrees. But remember, as the name implies, that this is a heat recovery chiller. Its primary function is to provide sufficient cooling capacity at a specified leaving water temperature. The heating that you get from the chiller is an additional bonus. Remember that this is still a high lift chiller. Depending upon your desired heat recovery temperatures, good unloading for a heat recovery chiller may be 50% part load, or even as high as 75% part load.